Module 28, Likelihood and Bayes Theorem, Section 3, Probability Trees. So this probability tree is a very intuitive way to visually represent the probability of any event, and you can use this tree like illustration to solve a number of probability problems, especially in population genetics, that we will see in this section. So in the probability tree, every tree has an origin. So it's something like a graph, the coordinate system, there is an origin. Just like that, from origin the probability will sprang out. So usually it's only two branches that comes up. So along the branch you write the probability of that event, and the leaf of these trees are nothing but the outcomes, So for example, coin toss experiment. So from origin there will be two arrows going. Each arrow you are writing on the edge you are writing, or the branch you are writing the probability of getting that outcome. For example, there are only two outcomes for the coin toss, head or tail. So to get head, the probability is 0.5, so you are writing the 0.5. The second one is also, the tail is also 0.5, so you have to write the 0.5. So usually in the probability tree, to calculate the total probability, you have to multiply along the branch, because probability of event A and probability of event B is equal to probability of event A multiplied by the B, given that A has occurred, right? So you have to multiply along the branch and then add it. So all these values. So if you do this addition of all this probability of any probability tree, the answer is 1. So the combined probability of any, these kind of things will always be 1 if there is no, further changes into the probabilistic system. So if it is non-random, then it won't be 1, but if it's random, it is 1. So that is what the principle of Hardy-Weinberg equilibrium in population genetics, that we will see that lately. So you just have to multiply, then you have to add it. So that is how the probability tree works. Let us consider one example, because the probability trees are really helpful for population genetics problems. The example here is that offspring of heterogeneous parents, heterogeneous means dominant and recessive allele, so the capital letter A and small letter a, so that kind of things are called heterogeneous or heterozygous. So the opposite is homozygous, that means that both are dominant or both are recessive, both are capital or both are small. So why these two things? So as you know, most of the animals or plants are diploid. So that is why the alleles, there are two sets of alleles or two sets of genome in human beings or diploid plants, That is why these two things are coming. So offspring of heterogeneous parents with one dominant allele and one recessive allele, what is the probability of an offspring having at least one recessive gene? So what is the probability of having an offspring with at least one recessive gene? At least one recessive gene means small a, Next part of the same question, what is the probability of having an offspring with recessive phenotype? So to have recessive phenotype, you need both to be recessive. Both alleles have to be recessive, then only you are going to get recessive phenotype. That means small a, small a. Let us solve that on the board. So from the origin, you will see that there are two arrows going. That is nothing but the gamete selection. So the first type of gamete is the female gamete. So let us put like this. This is a female gamete. So there are two kinds of female alleles in the female gamete. So it is either capital F, that is dominant, the small f is the recessive. So the probability of this dominant and recessive is nothing but X and Y, right? So that is the probability of forming the recessive, as well as X is for the dominant allele. Now the selection of male is the next step. So male gametes is the next step. So again two arrows. This will also male two arrows, right? So from this as well the two arrows will go. So now this one is basically X and Y. This probabilities are all same here, X and Y. The genotype frequencies are all same here. Now coming to the genotype. So first is genotype. Next is phenotype. So what is the genotype on this case? So here the male gamete determination is, first is F, both are F, that is capital F, right? The capital F means it is dominant. Then the male can be dominant or recessive, the M, capital M is the dominant, while this one is small m is recessive. So it is basically small m, right? So in this case, capital, these both are actually the, the F allele is basically the recessive allele. So it is small f. Again the male alleles can be capital M or small m, right? Small m. So let me put this into small m once again. Right. So these are nothing but the genotypes. FM, 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 FM. So here it is double recessive or heterozygous recessive. This is heterozygous dominant, while the homozygous dominant, homozygous recessive. These are heterozygous dominant and recessive. So if I ask you at least one recessive gene, so recessive is a small letter. These are the capital letters are dominant. At least one recessive gene means all these are at least one recessive gene. Now, as you know, the phenotype here is, except this, all will have the dominant phenotype. So the phenotype is D. This is also D. This is also D. While this one is recessive phenotype. So that is what you have to know that. So this is the phenotype, while this is the genotype. Now the point here is that what is the frequency of X and Y? Usually the frequency is X is equal to 0.5, while Y is equal to 0.5. Now if you can calculate, total frequency is basically 0.05 and 0.05. So you can actually convert that 0.05, 0.05, all this together. So if you calculate, the combined frequency is going to be 1. So that is what x square plus 2xy plus y square is equal to 1 is basically Hardy-Weinberg equation. So that is exactly what it is. Now if I ask you at least one recessive gene, so all this one, so how will you calculate? So this is 0.5, 0.5, this is also 0.5, 0.5, 0.5, 0.5, 0.5. So this way is 0.5 multiplied by 0.5 is 0.25. 0.5 multiplied by 0.5 is, this path is 0.25. 0.5 multiplied by 0.5 is 0.25. This is 0.5 multiplied by 0.5 is 0.25. So if I want to calculate the combined probability of 1, 2 and 3, it is nothing but plus. As I told you, this is all multiplication, while column below is always plus. So 0.25 plus 0.25 plus 0.25 is equal to 0.75, 0. That is what the combined probability is basically. So all these probabilities you will have to add it to get the combined probability of that. Okay. So basically that is how the at least one recessive gene is all about. So if you're saying that if you want 1 and 1 and 1, so then you will have to multiply these probabilities together, right? Or and that is what the difference here is all about. So the Hardy-Weinberg equilibrium is nothing but x square plus 2xy plus y square is equal to 1. So what does that mean? X square, because x into x is x square. So 0.25 multiplied by 0.25 is 0.025, right? 0.5 multiplied by 0.5 is that is what you're going to get, 0.25. And then 2xy is basically this one, x and y, xy, xy, x and y, x and y. So this value, this is 2xy is this value and y square is this value. So if you add all these together, 0.25 plus 0.25 plus 0.25 plus 0.25 is 0.75. So that is this entire value is 1. That is what, without without any selection or recombination, the frequency never changed. So that is that is what it says. Now recessive phenotype is only this. So how much is the recessive phenotype? The frequency of the recessive phenotype is nothing but the y is 0.5 multiplied by 0.5. So y square, 0.5 multiplied by 0.5 is nothing but 0.25. So that is the answer to that question. So if you're asking recessive phenotype, it is going to be 0.25. So this sort of the probability diagrams, the tree diagrams are really useful for making the calculations very easy. Let us consider another problem. Suppose a given gene is not sex linked and has two alleles of which one is recessive. If 4% of randomly interbreeding population shows the recessive phenotype, what is the probability that an individual in the population with the dominant phenotype is heterozygous? Let us solve that in the board, whiteboard number 8. So in this case, what we know is that the R is the recessive phenotype. The recessive phenotype is 4%. 4% is nothing but 0.04 is the probability. So this much we know. So how did we get this 0.04? Y multiplied by y is equal to 0.04. So that is nothing but y square. So let me write here y square is 0.04. So y is equal to root of 0.04, that is equal to 0.2. So we know that the y is 0.2, x is 0. X plus y is always 1, the frequencies. So this 1 minus 0.2 is 0.8, right? So this one is 0.2, x is 0.8, 0.2, 0.8. So that way you can calculate the rest of the probabilities, or you can also use the equation. It's very simple. X is equal to 0.8, we know y is equal to 0.2. Right. So now what we have to calculate is the 2xy. So these values, dominant phenotype which are heterozygous, or heterogametous dominant phenotype. So that is nothing but 2xy. So let us now easily calculate using the tree. 0.2 multiplied by 0.8. Plus 0.2 multiplied by 0.8. So this 2 together is basically 0.32. Fine. So that is basically 0.16, 0.16. So together you are going to get 0.32 here. So this is our answer. 32% is the thing. So otherwise 2xy, x we already know, that is 0.8, 2 multiplied by 0.8 multiplied by 0.2 is equal to 0.32. So this is the same answer that you are going to get through the tree like illustration as well. The probability tree is really helpful for grasping the fundamentals of the population genetics. There are several assignments for your homeworks, whatever you call these homework. You have to actually put that into the discussion sections. I will be looking each and every one of your answers, correct or incorrect. The first problem here is that if 91% of the population shows dominant phenotype, what is the probability of having a homozygous individual showing dominant phenotype? Problem number 2. If 49% of population have dominant individuals with homozygous genotype, what is the probability of having a recessive phenotype? Assignment number 3. If 16% of population have recessive phenotype, what is the probability of having a heterozygous or heterogeneous individual? Next problem. A patient goes to see a doctor. Doctor performs the test with 99% reliability. Doctor knows only 1% of population is sick. If patient tests positive, what is the probability that she or he is sick? So it's the same problem that we have seen that in earlier section. You have to solve this problem with probability tree. Let us see how we can do that, an intuitive solution to that, in graphical solution to the same problem. Let us solve that on the whiteboard. So in this case, let us actually sprout the two arrows from the origin. So the first one, let this be disease. So here it is sick, healthy. So again, two arrows will go from here. So this is nothing but test. So test says positive or negative. So let this be negative. This is positive. And then this will also go two ways, positive and negative. So negative and positive, whatever it is. So you can say that way. So what we know is that of the whole population, 99% are healthy. So that is 0.99 are healthy, while 0.01 is only sick. This much we know very well. And of this one, the test is because the reliability is that positive detection of positivity is 99, that is 0.99 is the test says positive for the sick people. The rest is 0.01, that is the false positive, the false negative, it is negative for the sick people, right. Now for the healthy, the test says negative, majority is test says negative, so that is 0.99. So this is true negative, while this is basically false positive. False positive is basic again 0.01, right. So we can multiply these values to get what is the total values you are going to get. So let us start from here. 0.01 multiplied by 0.01 is basically 0.0001. That is nothing but false negative. This is negative, but these are sick. So these are false negative. So 0.01 multiplied by 0.99 is basically, these are the true positive. This is nothing but 0.0099. This is true positive. Why true? Because the positive and they are sick. Now this is that the test says positive, but they are actually healthy. So it is basically false positive. 0.99 multiplied by 0.01 is basically the same value. 0.0099 is basically nothing but false positive. Now finally 0.99 multiplied by 0.99 is basically the true negative. True negative is nothing but 0.0198. This is true negative. Now what we have to find is the fraction of the false positive. The true positive is 0.99, false positive is 0.99. So fraction of false positive out of the total. So this is the false positive out of the combined positive. So what is basically fraction of false positive or fraction of true positive? In this case both are identical. Is basically let us say false positive fraction is Fp divided by Tp plus Fp. So that is basically 0.0099 divided by 0.0099 plus 0.0099. So that is basically, if you plus these two values, you are going to get 0.0198. So 0.0099 divided by 0.0198 is equal to 0.5. So that is the same answer that we got earlier using our equation. So this is a very very easy way to calculate that one. So it is basically, the calculation has to be based not on the false positive but on the true positive, because we are now testing that the truly sick, right, if it is positive. So it is basically true positive out of the combined positive. So which is a true positive? This is a true positive. So true positive out of the combined positive is the test. So that is what we are trying to detect. So true positive out of the total positive, so 0.5 only. So as you see, it is very low chance. So the intuition doesn't work most of the time. So assignment or homeworks continues. A patient goes to see a doctor. Doctor performs a test with 99.99% reliability. Doctor knows that only 0.1% of the population is sick. If the patient tests positive, what is the probability that she or he is sick? Next assignment. AIDS affect 1 in 100,000 Indians. A new test kit is developed which is 99.9999% accurate. The test never generates false negative but generates 1 in 10,000 false positives. If patient tests positive, what is the probability that she or he is sick? Next problem. If dangerous fires are rare, there is only 1% of the dangerous fires, the frequency, but the smoke is fairly common, 10% smoke you can see in the household. due to the barbecue. So the barbecues are quite common, or using the old style wooden chimneys. You can see the smoke. And 90% of the dangerous fires make the smoke. So we have several of the information now here. 90% of the dangerous fires make the smoke, and the dangerous fires are very rare. There is only 10%, but smoke is fairly common, 10%. And dangerous fires are only 1%, right? Now the question here is, what is the probability of dangerous fires when there is a smoke? Dangerous fire given the smoke. You can solve this using a Bayes equation, Bayes theorem. Let us do that in the whiteboard. So what we have to calculate is the probability of fire given smoke. So this is the probability that we would like to calculate. So this is equal to probability of smoke given fire. So this is the likelihood, basically smoke given fire multiplied by probability of fire. So this is nothing but prior probability of the fire divided by prior probability of smoke. Right, so this is how to solve for the posterior probability of the fire in case of the smoke. If we detect the smoke, what is the posterior probability that it is actually it is caused by the fire. So let us actually see that, because this value is probability of smoke in case of fire, as we already seen that it is 90%, so we can even say, write in a percentage also, multiplied by probability of the fire. As we know, it is only 1%. The problem says that it is only 1%, divided by prior probability of smoke. Again, the problem clearly state that directly it is 10%. 10%. So 0 goes. Then if you solve it, it's nothing but it's 9% is the answer. So 9% or 0.09 is the probability, which is very, very low. 9% chance that the smoke is really caused by the fire. So this kind of problems can easily be solved using Bayesian theorem. Another problem: you are planning a trekking today at Paithal Mala, but the morning is cloudy. By the way, Paithal Mala is a hill station in Western Ghats, and my house is pretty near to this hill station, the Paithal Mala in Kannur district in Kerala. 50% of all the rainy days start off cloudy. That is our prior information. You see, 50% of all rainy days start off cloudy. But the cloudy mornings are common. About 40% of days start cloudy in Kerala. And this is usually a dry month. So the month in which we are planning for the trekking to the Paithal Mala is a dry month. So only 3 out of 30 days tend to be rainy, or only 10%. So these are the prior information. We have to calculate what is actually the chance of getting the rain today. Let us solve that on the board. So what we have to calculate is the probability of rain given clouds. So this we have to calculate. So is equal to, the opposite is the likelihood, probability of cloud given rain. So multiplied with prior probability of rain divided by prior probability of cloud. So both of these are prior probability, while this one is posterior probability. So we know that probability of clouds given rain is equal to 50%, because the problem clearly says so. Now multiplied with prior probability of rain is also given in the problem, straight away it is 10%, divided by prior probability of the cloud is also given straight away in the problem, that is 40%. So to solve this one is actually very simple. For 0, 0 gone, then it's basically 50 by 4 is nothing but 12.5%. So that is equal to 0.125 is the probability. It's very, very low probability that if you see probability of rain in case you see the cloud. So if you see the cloud in Paithal Mela, so the chance is that it will rain is very less. Only 1 in 10% opt for a middle berth in sleeper class of Indian Railways. By the way, the same problem we have seen that in the probability when we discussed about the probability. I asked you to calculate the probability of this getting a middle berth, if you remember it right. By the way, what is so special about middle berth? Apparently, I like middle berth rather than upper berth or the lower berth, But fortunately, not many people opt for the middle berth. Only 1 in 10% opt for the middle berth. So what is the probability of getting a middle berth in the sleeper compartment? That is the question here. Given the information that only 1 in 10% opt for the middle berth, you have to calculate to get the chance of getting a middle berth if you opt for it. So as you know, in every coupe there are 2 middle berth out of total 8 berth. So you can calculate the normal probability and you can update that with the prior probability using the Bayesian theorem. Try to do this work yourself and later come to the solution. Let us calculate that on this board. So in this case, what we have to find is probability of middle berth given reservation, right? So this is what we have to find, the posterior probability of if you reserve what the probability that you will get the middle berth. So that is equal to the reverse is nothing but the likelihood. So that is basically probability of reserve given middle berth. So probability of getting reservation given that it is actually the middle berth multiplied with probability of middle berth by probability of reservation. So these are nothing but prior probability, while this one is a posterior probability that we are going to find out. So this one is that the trickiest point here is the probability of reservation. So this the denominator. So how do you calculate this denominator here? So this is by the combined, the law of total probability is nothing but probability of reservation is equal to probability of reservation given middle berth. So this is the same thing, the likelihood here. Middle berth multiplied with probability of the middle berth plus probability of reservation given no middle berth multiplied by probability of not getting middle berth. This we calculated, if you remember, it is actually 0.75. So this one is equal to probability of reservation in case you opt for middle berth is 0.25. This is we actually solved this one in the probability theory. So to get the middle berth, if you opt for reservation is 0.25. So you have to multiply this with probability of getting the middle berth, because 90% people do not opt for the middle berth, it is 0.9. So plus not getting, so this is to get the middle berth, and now not to get the middle berth is nothing but 1 minus 0.25 is nothing but 0.75, that is A prime multiplied with, so this one not getting the middle berth is the rest of the thing, so 10% is the chance, so that is basically 0.01. So if you solve it, it's nothing but this value is 0.225, this value is 0.075. So if you plus these two values, you are going to get 0.3. So 0.3 is this value. So let me write here. So this value is basically 0.25. As you see, this 0.25 is nothing but this value or this one. So this is nothing but the likelihood, 0.25 multiplied with the prior probability of middle berth is nothing but 9.9. So 90% people, right? So this is nothing but 0.9 divided with the denominator is prior probability of the reservation that we just calculated, that is 0.3. So if you calculate that, you are going to get 0.75. As you see, 0.75 is quite a high chance that you will get the reservation. So earlier we started with 0.25. So 0.25 was the actually as calculated by the Laplace probability of proportion of the success. But you see that 25% is very low. But after this prior information that only 10% opt for the reservation opt for the middle berth, the rest 90% do not opt. So now you see that magically the probability of getting middle berth has increased. So this is the beauty of the Bayesian theorem. So in summary, probability trees enable an intuitive visual representation of events in probability space. Probabilities of each events are written on the branches, while outcomes are on the leaves of the trees. To calculate overall probability, we multiply probabilities along the path and add the resulting probabilities down the column. So that is how to work with the probability trees. Thanks for watching.